Hello, 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 hello. So what we have here today is problem set 9.2, problem number 1. Now, the book gives you this formula. This formula is true, but it's a little confusing. And let me give an example where it's confusing. As you're coming down, imagine you're driving down a road really, really fast, and you've got a air bubble in your brake line, and you're pressing the brakes, but you're not getting a lot of action. And up ahead of you see a runaway truck ramp. So you pull off onto the runaway truck ramp. You're trying your hardest with the brakes, but ultimately you're saved by the fact that the truck ramp goes up, and about 80 meters up, you've stopped. You're safe. Your brakes are still a little hot, and you survive. But let's think about what's going on here. As you're going down here, you got lots of kinetic energy. You find the truck ramp, you start going up. You start turning that kinetic energy into potential energy, but you're also at the same time turning into heat energy. So kinetic energy is dropping, potential energy is increasing, as is heat energy. Now, if you use this formula, it will be correct. Of course, you got to remember that the change in potential energy is positive, and whatever the kinetic energy, that's a drop in kinetic energy. A lot of people find that a little confusing. So I'm going to actually go back and look at one of the formulas we have in the past, which I think you might find a little easier. So, remember you have this one. Mechanical energy initially is equal to mechanical energy finally. That is generally true. Although in the real world it's just not true. But in the real world, we know that energy is not created or destroyed. The initial energy will equal the final energy. Initially, we start out with kinetic energy, which is 1/2 mv squared. And in the end, we end up with two types of energy. We end up, well, hold on. Let me just, in case we start out with kinetic energy is what we have initially. And in the end, we have potential energy and also internal energy. Usually in the form of heat, but not always. So, start out with kinetic energy, you end up with the final energy. My question is, how much energy is in the form of heat? So you've gone up 80 meters. So that's the basis upon which we're going to figure out the answer. So kinetic energy is pretty straightforward. 1/2 mv squared is equal to, now the potential energy is mgh plus u, the final heat energy and final internal energy. Now, my car's mass is equal to 15,067 kilograms times my velocity. It's an economy electric car, even at the max speed. It's 42 meters per second squared, and that equals my car's mass, 1567, times gravity, earthlings, 9.8, times the height. We said it was an 80-foot or 80-meter ramp. And then, of course, we got UF. Are we ready? Well, let's start solving. So, half of 1567 is 783.5 times 42 squared is 1764. And that's going to equal, now my mass times 9.8 is the weight in newtons, which is 15,356.6 newtons times the height will give me the potential energy. And there again is our internal energy right there. Okay, multiply these two together, and I get that my total kinetic energy before I hit the ramp was 13,682.94. That doesn't matter as much because when we round it, a lot of that stuff ain't going to make a big difference. The total, our weight times our height, gives us our potential energy at the end when we stop rising, and that gives us 1,228,528 plus the internal friction. Now, got these on both different sides here. I need to subtract. Subtract 1, 2, 8, 5, 2, 8. Subtract 1, 2, 2, 8, 5, 2, 8. And what I end up with is, at the very end of it, I've got 153,566 joules is equal to the internal energy. That's the total friction. Now, by the way, 153,000 is a big number if you're talking about money. It's not a big number if you talk about energy. This is an amount of energy that most of us would burn through in an hour of an ordinary day. Well, about an hour. Yeah, about an hour, less than an hour of an ordinary day. So it's not a very big amount of energy. It's but I set this up with my car in mind. Now, your car will possibly be heavier, which would make this number slightly heavier, but not so much because you add mass here, but you're also adding mass to the number you're decreasing. The thing that's going to really affect your number is the velocity. Mass is on both sides, so mass cancels itself out to a certain extent. But velocity is only on one side, and it's squared. So if you've got a faster car than mine, a car with a greater max velocity, you're going to have a much bigger amount of heat that's being produced at the end of stopping. In fact, you could easily have 50 times as much heat. Well, maybe not 50 times. You could easily have 20 times as much heat. The point is, you're going to have a lot more heat probably. Now, one or two people have had a car that's actually slower than mine. I would never have imagined that somebody would have a car slower than mine, but some people do. In that case, the problem doesn't really work out because what they find is they start getting a negative number. Well, how can they get a negative number? Is their car getting colder? Well, no. And in that case, if they have a lower max speed, they'll have a lower kinetic energy, and they just simply would never have made it up 80 meters. They would have come to a stop without any brakes long before then. I designed this experiment with this problem without ever thinking that anybody could have a car slower than mine. So, if you do have a slower car than mine, I apologize. If you have a car that's faster than mine, expect that your number will be greater. Okay? Have a nice day. And drive safely.